In the previous lecture, we saw how to solve a system of linear equations using Gauss-Jordan and Gauss elimination method. In Gauss elimination method, how do we solve is we convert, this is the matrix equation, the equation matrix corresponds to this. We try to use these row operations and we try to convert this lower triangular, the lower element to be make it to 0, and then it becomes upper triangular matrix, and then we can solve by the back substitution method. So how we are doing this? That's what with this step we found. So what we did, so first we want to make this element to be 0. We will make one by one element 0. To make this element 0, what we have to do, you have to subtract this row 2 with this element divided by the diagonal element, the first above this element, and then multiply that factor with the row 1, and when you subtract, this element will become 0, and this operation has to be performed over the entire row as well as the B matrix, and that's what we are doing here, and we got this change in the matrix equation. Okay, so this makes this first element 0, and then we have to proceed for the next one. So how we should remember how we are starting. We are starting with the row 2, and then we are going to row 3. So the row 3, that is this element, we have to make it to 0. So again the same thing, we take the row 3 minus, and see this first element is the one which we want to make it to 0, divided by the diagonal element 10, and that makes this also, this modifies this entire row. Now after performing this, now we have to go, the next is this element has to be made as 0. So what we are doing, so this element divided by, now we have jumped to the second column, correct? We are working for this, making the second column 0. There we will go for the second diagonal element. So then this diagonal element is divided here, and then with this operation multiplied over 3, we will get this as a, now we gotten finally an upper triangular matrices, up matrix. So now after attaining upper triangular matrix, the solution is simple, because then you z equal to 3.5 by 2.5. This is what we call as a back substitution. That's what I have written it here. So now, so this operation, if you write in the form of an algorithm, what we will see is this. So this is the algorithm which we are using to modify our row, to make it, every row is basically performed like with this algorithm performed, and this will make this this element 0 one by one, and after getting this upper triangular matrix, this is the back substitution algorithm. We don't have to explanation, it is very simple. Okay, so this is the two algorithms which eventually perform the task of upper triangularization and solving the solution. So now let us try to see the program which solves this matrix using this Gauss elimination method. So, and here is a simple program. So what I am doing is I am defining this matrix here. You can see this is the matrix B vector and the solution vector, and I am using another variable pivot. We will come to it later on. This is for test. Let us skip it. So now what happened? I am giving the matrix. Okay, let me read this matrix element from input X. Fine. So what I mean, input is a file. So and the input file is given here. You can see. So the input file is given as a 1, 2, 3, 4, 5. 5 cross 6 matrix, but it is not 5 cross 6 matrix, it is 5 cross 5 matrix, and the last column I am giving it as my B vector. Okay, so this matrix gives a complete your matrix as well as B vector. So this is what I am asking for dimension n. So we have to give the dimension, it will read from here. So this n is used everywhere. So see, even though I given a 5 cross 5 matrix, even you can, this will work for 3 cross 3 also. When n equal to 3, what happens? It reads only these 3 rows and the 3 columns and the B vector. So it still works. Okay, so it doesn't matter for us. It can be, it should not be greater than 5 because we are given the maximum of 5 cross 5 matrix. So now what happened here? This is what I am reading this matrix. Okay, how I am reading the matrix? We can, this is simple. This reads in a line, and then I am printing the matrix. So let us first see whether my matrix is read properly and printed properly. Okay, so I am going to compile. So let us compile this Gaussian./a.out. Okay, so I'll give a 3 cross 3. I'm not going to do 5. Let us see 5. 3 cross 3. So you can see. So this matrix is read properly. What happened? 10, 1, minus 5, 10, 1, minus 5, and 5, and minus 20, 3, 20. So this is perfectly reading the matrix nicely. So up to this line, so even we have printed the matrix. Now I am going for the triangularization. Okay. So how we are going to do the triangularization? So let us come back here. So let us see. So this is, so remember, so this operation. So this operation in each row, this corresponds to not a one element, all the element of the row as well as the B. So this, so what, this one line itself is a loop which performs operation over all the elements. So that's what we are doing here. So this operation is written in these lines are the one which performs this operation here, and outside the loop I am performing it on the B matrix also. This completes the operation which is I am going to make it on every element of a row and a column. So in this, when I use this algorithm, this makes this first element to be 0. Okay, that we checked anyway here. Okay, and then this is something interesting, something important we should know is, so after this, the second loop comes, because it's not only I have to make this element 0. First I make this element 0, then this element 0, so this completes. So I have to perform again an operations over the column. So this is another loop. So one loop is perform the operations all over the element of a row. Another is one by row I have to do it. So that is another operation. So that operation is taken in the outer loop. So this is the loop which performs zeroing of one particular column. Why we have, this is interesting thing, why we have I plus 1 to n. So this is interesting. So why we have I plus 1 is, so if you see back to here, so when you are doing for the first time, you start from, for suppose first column you are doing. What will you do? We'll start from the second row itself, you make it to 0. You don't make it from first, diagonally you make it to 0. And when you jump to the second column, you make it from third. Correct? So if I have 5 columns, then you go to third, you make it from fourth. So you always make the ith column, you make it one step, one row ahead of this ith column. So I plus 1. So that's what we are given here, I plus 1 to n. So this one, so what happens? So I plus 1 means this one. So this, this loops performs this zeroing. Okay, and after completion, this zeroing. Okay, fine. So now then comes, and I shouldn't stop from there. After zeroing this one, then I have to jump to the next element here. That has to 0. That means now my column should go to second column, and that's what performed in the outer loop here. So this outer loop, which eventually there will be n columns, so we keep running for all the n columns. At the end of this loop, you will get a nice triangular matrix. So let us see whether this matrix is coming or not. Here itself you are seeing. Okay, so you are seeing here. So the second one, if you see the bottom elements. Okay, so it has made all zeros. Okay, leave this one. This is B matrix. So now here we got a nice upper triangular matrix. Okay, so up to this part of the program, this works fine. It creates an upper triangular matrix, and then we have printed the upper triangular matrix also. That's what we checked right now. And then we have to go for the back substitution. The back substitution algorithm is here. So if you see the back substitution algorithm, So it goes from, so there will be a summation, okay, and this summation basically, see, this actually goes from backwards. I have written as I plus 1, but yeah, you can, you can actually do it out. It goes backwards because back substitution will actually go from first you find out z, then y, and then x. Okay, so you can test, you can put it easily. So backward means I goes from, I should written I goes from n minus 1, n minus 2, n minus 3. Okay, so then what happens? So if you see x of I, that's x of n, that's a z element. X of n will have the nth diagonal element, that is this. Okay, and b of n, that is this, and j is I plus 1. So n plus 1, there is no term beyond n plus 1. So this will be completely, this will not be performed at all. So we get b of n by a of n, that is this portion. That's what here 3.5 divided by 2.5. And we need to go to next one. You can just try to operate it from here. Actually, I should have written that. The point is, so n, your I is n, n minus 1, n minus 2, n minus 3, go on up to 1. Okay, so this is the way that I should go, and then this operation also we can perform. So this is what I have eventually converted into the back substitution part. So if you see here what we are doing, so we are going from n to 1 in the reverse way, descending order, and then this is the first sum I am going to calculate. So this sum I am initializing with 0. I initialize to 0 here, and then I am just adding this with this a of ij into xj, and that's what I am doing here. Okay, so and you can perform, you can see the first term when it starts with, this term will not be there at all, because when I starting with I equal to n, this goes from n plus 1 to n. Okay, so this loop will not be performed. You don't need this xj at all. Okay, so even though it appears this code is complicated because I am using xj before I am calculating xj, it doesn't matter. It works fine. Okay, and then after doing the sum, and then this is I am doing this, just the same operation here. Okay, so and after this procedure, it is going to give me the solution xi. Okay, so and this xi. So now I want to test whether this xi is correct or wrong. Okay, how to do it? Again, multiply this. Basically, how to do it out? Multiply with this matrix, because the matrix A, multiply the solution of I should get back the B. So that's what I have to do. So, but now I have already manipulated my A matrix so much, my A matrix doesn't exist anymore because I have modified this A matrix because of all these operations. So I need to read it again. So what am I doing for testing? I am reading this matrix using the rewind command. Reading from the same file, taking the control to the first line. What is the 11? If you see here, 11 is the unit number in which we are reading the input. So I am rewriting, after reading this files, the control is here right now. I have to take back to first one and start reading this element, and that's what the rewind command does. So then I am again reading this. What am I doing? I am reading one by one. This line, so this line reads the first row, correct? The first row, and then, and I know my x and y, right? All the solution I know. All I have to is multiply each element with the corresponding x value, and that's why I'm taking this sum and taking the sum equating to 0, then sum multiplied by this element what I'm reading, multiply the corresponding vector. And so after the end of this loop, that means I have performed the entire sum. This entire sum I have performed. So now, and that should be, so this sum should be matching with our B matrix what we are given. Okay, so this is what we have to see. So let us see. So I am printing here sum and the B test. Okay, so already I am printing here the solution again here, and let us see. Okay, so this is the solution we got. Okay, this is a solution we got, and I am multiplying the solution with the matrix A, and the testing gives me the same number. Okay, you can see here. So the solution is 5, 5 minus 30, that is 16. So this program is nicely working. We tested it for 3 cross 3. But anyway, our matrix can be given for more than 3 cross 3 also, because we are given here 3 cross 3 matrix. We are given 5 cross 5 matrix. We took only 3 cross 3. Let us try for 4 cross 4. So let us see whether this works for 4 cross 4. So I am going to give dimension as 4. Perfect. So it works. You can see 10, 20, 3, 4, 4, and these are the solution vectors. The 4 solution vectors I got here. 1, 2, 3, 4. Okay. So, and let us see whether this works for the 5 cross 5 matrix. Perfect. It works. Okay. So it works here. Perfectly works. And this is a solution vector. Fine. So this program is actually working very nicely for all the matrix problems we are solving. So this is a working program. We can use it for different matrices also. This will work. So now, let us try to use this to solve another problem. That is this problem, a very simple matrix, 3 cross 3 matrix. But let's see whether this program is able to solve this matrix. So what am I going to do? So instead of that input, I have already created another input. The name is input 1, and this I given 10, 1, minus 5, 1, minus 20, minus 2, 20 and 2, 5, 3, 5 and 6. So this input file, let us see whether this program what we developed can solve this matrix or not. So I have to change the file name. Initially it was input. Now I have to make it to input 1. Okay, so now we will try to solve for this matrix. So remember, this code is working very well for this matrix. Even if I change 1 or 2 elements, you will see it will come to be, it work very fine. So let's do for simple problem. So I am going to run, I am going to compile the code and run the matrix. So this is a 3 cross 3 matrix. I am giving 3, and there it goes. See, it gives. So this is not working for this particular matrix. So somewhere else some infinity comes, and then that messes up your solution, everything, and you are not able to solve this matrix. That means what it says is this code what we wrote is not a trustable code. For some matrices it fails, but remember, this matrix is not a singular matrix. This matrix, if you do it in a pen and a paper, you can actually solve this matrix. This is a solvable matrix, not a singular matrix. It has a unique solution. It works very fine. The numbers, the matrix is not using very big numbers, so it can create round off errors, all those problems. Nothing, very decent numbers and not too many numbers, only 3 cross 3 matrix. And the code what we develop, it fails. So that means there has to be something is happening in the code which is making problems like given by these types of matrices not working. Okay, so let us try to understand why this is failing, and let us try to see from the algorithm we have used whether this algorithm is incapable of handling certain matrices, these types of matrices. What happened? So this is the algorithm we were using for the upper triangularization. Okay, so and what we are doing, so we are performing this first operation. So after performing the first operation, we want to make this element to be 0. Well, that element has already become 0, and then I am performing the next operation to make this element 0. What is that? This element 0. We have to perform. Okay, so let me perform it. So yes, perfect. This also made this element 0. Now we have to make this element 0. So I have to use the same algorithm is used in the computer. So it puts up this algorithm. Now if you see here, what am I doing? I am dividing by A22. And this A22, if you see, that is 0. So therefore, at this when the code reaches this stage, it finds something divided by 0, and at this step the code crashes because you are getting something divided by 0, and that's what you are getting, the infinity and NaN and all those funny warnings and all. Okay, so so how do we, so now, but we need to solve this problem also, because we can't allow this, because this is a very well posed problem, and if your computer is not able to solve this problem, there is no use of the code. During the process, anytime some matrices it will be solved, some matrices it will not be solved, we can't do it. So we have to find a solution to this problem. And why this problem happened is because the diagonal element is becoming 0. So this, all this algorithm, even if you go back to that back substitution algorithm, here also you always divide by diagonal element. So in the entire matrix problem, this diagonal element is something very serious. Okay, so we should make sure the diagonal element will never become 0. Okay, so and this process of making sure the diagonal element never becomes 0 is called as pivoting. So how we are going to implement pivoting in our program, in our code of solving these linear equations. Okay, so the first we will look for a very simple pivoting. What is that? That is called as a partial pivoting. In a partial pivoting, what we do, so this is the same matrix I am using, the same matrix equation we are doing. So we wanted to solve this problem, correct? So what we are doing is, so means we want to make this first, this element 0 and then this element 0. Okay, so what will we do? Okay, fine. So then for this one, I will pick up the matrix and take this first column and see what is the maximum magnitude element in the column. So here if you see, this 20 is the maximum magnitude element in the column. So then I am allowed to do these row operations. I will swap these rows. Okay, such that this maximum magnitude element come and sit in the diagonal. Okay, so that's what I am doing. I am doing this. So I swapped the rows so that the maximum diagonal element comes and sits. So maximum magnitude element will now become the diagonal element. So and then I perform this operation, and that gives me these two operations will make it to these two elements 0. Okay. And then next what am I going to do? Now I want to go for this element to be 0. Then I look for this submatrix. I will pick up this submatrix. Then again take the column corresponding to the first column, which I want to make it to 0. I will see this is the element which is the maximum magnitude element. So now I have to swap it here and here. Okay, so when I do it, I get this. Incidentally, this itself gave a solution. Many times this may not give a solution. Okay, so not 0, then you'll have a number, and this is what will happen. Okay, so now you can think, now I am doing a row swapping in a submatrix. It doesn't really change the solution. The reason is because these first two elements are 0. It doesn't matter. Okay, so therefore this operation what I am doing is allowed. But it's a allowed operation which will not change my solution. So by this operation, I can always make sure any column I make sure when I performing any operation on any column, I'll always make sure the diagonal element is a maximum magnitude element. So it will never become, that's very unlikely it becomes 0. Okay. And this is not also, there are cases this pivoting also fails, okay, because especially when your certain columns contain, the elements are very small numbers. Elements of a certain columns are very small, then this also fails. This is, okay, most of the cases partial pivoting works, but under rare occasions partial pivoting also fails. So then what we have is something is more rigorous than this, that we call as a full pivoting. In a full pivoting, what we are doing is, we don't take a column. we see the complete matrix and see what is the maximum magnitude element in the entire matrix. So there are two, 20 and minus 20. So if your algorithm is made like to scan like this, it will first end up this one, so it will make this as the maximum magnitude element. So then what it does is, I forgot to tell you one of the one important thing. So that is here. Okay, so whenever you are doing this row swapping, and all, corresponding B also should be swapped. Okay, and this doesn't alter your XYZ at all. You can see when you write down the equation, all this swapping should be corresponding your B matrix also swapped. Okay, so now coming to next one. So in the full pivoting, you look for the maximum magnitude element. So here, though there are two elements, if your algorithm is like that, if it reaches first here, it sticks here. So this is the maximum magnitude element. And the approach is to take this element to be in the pivot element. That is the two diagonal. So here, incidentally, this is falling on the same column. So you have to only do the row manipulation. So when you do the row manipulation, so this element comes to 0 here, and then you can perform this operation of making this element 0, and then you are getting this submatrix. Okay, and here again I will look for here what is the maximum magnitude element. So now this is the maximum magnitude element, that is 10. Now I have to bring this element to here. So how am I going to do? There are two operations I do. I do this row operation. When I do this row swapping, this 10 comes here, and then I do, followed with it, I do a column swapping also. So that's what is tricky here in full pivoting. Okay, so what it means is, so then, then I do it out here, and then this column swapping will bring it to, see, that's what I did. Okay, so you can check it. So, and this number comes up. And now I have to make this element 0. Now it is allowed because this is a bigger element. So I make it and I got an upper triangular matrix. Now, important thing to remember, to note in this full pivoting is we are swapping the columns also. That means if I swap any two columns, my B will remain unchanged. The swapping will happen between the vector, solution vector. Okay, and this is something tricky because in the program I don't give you this vector. We don't provide the vector. Okay, what we do, we provide this matrix A and the matrix B. We provide only these two. And when you do all these column manipulations, what happens? You have jumbled everything. This whole vector here jumbled, and finally when it gives you a solution of x, y and z, they are not going to be x, y, z. We don't know which one is x, which one is y and which one is z, because you have done all this column swapping, so it's going to jumble out this one. So an important thing in the full pivoting is you need to track the index of the solution vector also. Okay, so even though you don't provide the solution vector, you need to know which index, which vectors are being swapped. Okay, so writing this program is tricky. You can try it out. Okay, so one can actually do it out. You have to create in the place of solution vector, create an index vector and see how this index is being swapped and all, and maintain that index. Okay, so this is the way full pivoting is can be implemented in the Gauss elimination or any elimination methods of solving the matrices. Okay, so now, so this is full pivoting is more rigorous than your partial pivoting. Okay, so and there's something I can always write down. Suppose for example, let me have this equation. Let me take this equation. What I'm having is x plus 10y minus 5z equal to 1 minus 20x minus 2y plus 20z equal to minus 6, and then 50x plus 30y plus 40z equal to 20. So in the matrix form, this will be 1, 1, 10, minus 5, minus 20, minus 2, 20, and then 50, 30, and 40. So this is the matrix we are having. Suppose if I want to perform a full pivoting, that means full pivot. Okay. So then what I have to do is I have to look for the maximum magnitude element in this matrix, and clearly you can see this is the maximum magnitude element, and what you will do is you will try to bring this element to the first as the first diagonal element. But this is actually fooling, because this is not the maximum magnitude element. So why this is not a maximum magnitude element is, if you see here, if you carefully see this equation is just multiplied by 10. This equation is actually 5x plus 3y plus 4z equal to 2. And similarly, this equation is minus 10x minus y plus 10z equal to minus 3. So these equations are basically full, because there is a common multiple in these equations. Okay, so because of this common multiple, sometimes what happens, your algorithm will choose this as a maximum magnitude element, and sometimes, most of the time it works, many times this also fails. So then what comes is something we call as your implicit pivoting. That's why I written the exact matrix here. So here, so in the implicit pivoting, so what happens? So this is taken as in the implicit pivoting, what you do is take every row, find every row, pick up the maximum magnitude element of the row. Here, the maximum magnitude element is 10 here. Divide the entire row with a maximum magnitude element. That means what? Your row 1 should be divided by 10, and here 20 is a maximum magnitude element here. So the row 2 has to be divided by 20, and here 50 is the maximum element. This has to be divided by 50. So interestingly, this operation will makes your matrix like this, and clearly your maximum magnitude element will be 1. And this is coding becomes very easy, because your pivot doesn't matter at all, because once you make sure the diagonal element is always 1, you don't have to divide at all. Okay, so that operation we can avoid it by doing this implicit pivoting. So always, so in implicit pivoting, we divide, we make each row the maximum element is 1, and then we perform the operation. Remember, this has to be performed at every step. Once I made this as 1, and then when I do the operation, when I got a submatrix, here again this may go greater than 1. Okay, then again I divide every row by the maximum magnitude element and make every time less than 1, and that way we have to implement the implicit pivoting of the implicit pivoting in the code we can do. So implicit pivoting is a kind of more rigorous pivoting, which most of the time it won't fail at all. Okay, so a very a good codes will always use the implicit pivoting method. Fine. So with that, I will stop this pivoting. How to introduce pivoting in the system of linear equations, and in the next lecture we will see some important we saw only a simple basic method, that is Gauss elimination and Gauss-Jordan Gauss elimination. In fact, they are not at all a good algorithm. There are much superior and much efficient algorithms. We will see in the next lecture a better algorithm, which is better than Gauss elimination or Gauss-Jordan, which we call it as a LU decomposition. This we will see it in the next lecture. Okay.